I will be starting shortly. Welcome everyone. This is David. This is Kingernorth himself with microcontrollers with Kingernorth. So let's jump right on in and have a look at what we're using today. Here's a zoomed up view of what we're using today. Today we're going to be talking about the brand new chip, which is the one located right here from Raspberry Pi Foundation. They've designed this new chip and this is their board. This is the Pico RP2040. So RP2040. So this is something new. And it's actually looking pretty good. This thing has a lot of interesting features, and we're going to be talking about a lot of that today. So let me go on over to my main page here so we can start bringing up some information about this thing. So here it is right here. So let's have a close look at what's on this board. So this is the actual board itself. This is the completed board. But this chip right here in the middle, this is the RP2040. So this is what makes it work. And if you notice, it has the Pi Foundation logo on it, and so does the board. This is their version called the Raspberry Pi Pico, and this is a format that they've used before. But this is their first venture into making a full microcontroller design and having it produced for use other than their Raspberry Pi that we're used to seeing, which is a full-fledged computer. Actually, right from the Pi 0 right on up to the Pi 4 are all computers. These are not. This is a microcontroller. So this is a big step up. So we're going to have a little bit of look at what makes this thing up. So let's have a better look at some of the hardware and why it's called what it is and what it's doing for us. So when I say it's low cost, I do mean it's low cost. This is the design of the RP2040. So this is right off of their website from the Raspberry Pi Foundation. You can get these notes. And what they're doing is they're talking about all the release history, and we can see that this has already been, the initial release started in January. The board was designed and put to construction in 2020, and then this is updated at the earliest that was the beginning of February. So just a couple of weeks ago they came out with it. They added some actually extra information that was missing. They do have a table of contents in here. This is a really nice document to go through because you can click on anything and it'll jump to it. And we're going to look at a couple of things before we go on, and we're going to see why they call it the RP2040. So this is what it is. This is what we're looking at. When we're looking at an RP2040, this is what's inside the chip. All of these features that are in here. One of the big features it has in here, it's actually got in here, and they talk about it right here. It says an RP2040 is a low-cost, high-performance microcontroller, which it is, and it's a flexible digital interfaces. Now, it's quite flexible. It's not, probably doesn't have all the features that some other boards have, but it definitely has features that no other board has. The biggest thing that's going on here, it has a dual Cortex M0 processor. Now, these processors are quite common. They're referred to as the M0. and it's actually the M0 Plus, so it would be, if you were looking at the Adafruit line of chips, you're looking for things that have M0 Express. Not the M0, but the M0 Express. The big feature is the fact that it's dual, and this is something that nobody else has really done. And the fact that we actually have two processors located inside of this chip here that's doing all the work. And that's where the 2 comes into it. RP would stand for Raspberry Pi. 2 stands for 2 processors. The 0 says it's an M0 processor. That makes me think that there, somewhere down the line we're going to see an M4 version of this. And the M4 would then be a 2440 or whatever else is after that. The next number in this is the 4. That represents how much RAM is actually inside of the actual chip, built right into the processor chip. And this one has 264K. Anybody who's familiar with Arduino will know that that's a lot. We're used to seeing 8K, 16K, 32K. A few are a little bit larger, 64K, but not 264. This is more common when we get into chips that are controlled using programming similar to what this one is capable of, and we'll get into what that is shortly. And the 0, I believe, has something, I forget what the 0 has to do with, and I'd have to look that back up. But it is a 133 megahertz processor chip, by the way. So it's very fast. Now, it doesn't run at 133, and that's based on the crystal. There's actually an external clock. There's a crystal that has to be connected, and this crystal is running at, I believe, around 125 megahertz, I think is where it's set. And you can overclock it a little bit to get up to 133 if you really need to, but 125 is really fast in this type of a world. The memory is broken down into 6 banks of memory, which makes it very quick. It's got 30 I/O pins on it, basically, which these are general purpose I/O pins. So these can be inputs, outputs. Not all of them can be used for absolutely everything, but there's a good selection of choices on what to program these chips for. 6 dedicated I/O are set up that are able to support SPI flash, and that's supporting XIP, which is a protocol. But SPI flash is what's used to attach SD cards, can also be used for connecting to other devices. Dedicated hardware for commonly used peripherals, it does. When we look down in this list of things that the peripherals has, it has the SPI, it has pulse width modulation, which is great for outputting. UART is another communications protocol. It's got timers, it's got a real-time clock. It's got I2C, which is a very common protocol being used to connect up a lot of our peripherals. I've actually talked about that on some of our shows. We've used I2C devices. It's also got analog to digital converters and TS, which I can't quite remember what it's for. That might be true sign. But it's limited on where it can be used. So those are some of these chips are going to be allowed to be programmed for certain functions. Programmable I/O for extended peripheral support. This is kind of a unique feature too. These are actually individually programmable, and this is where the timers kick in. And what that allows us to do is we can actually create custom protocols or additional protocols like I2S is one that they're looking at, and people are trying to work with it right now, and they're setting up programmable I/O to get that special protocol, so you can set up a data channel for it to work in a specific way. So that's really neat. That's a really strong feature. This programmable I/O is going to allow us to move this further on down the line. It's actually built into the chip. There's 4 channels analog to digital conversion. This is primarily for inputs. So what this is, there's also an internal temperature sensor. So this is analog signals that are converted to digital. And this gives you a 12-bit conversion number, which is pretty common in these more modern processors. Arduino did it, but they only used lesser. In fact, if you remember in the Arduino line, you had to convert from 1023 was the maximum resolution, so it went from 0 to 1023 when we were looking at an analog input in the standard Arduino chip.
in the standard.
Whereas in the more modern ones, we go up to 12-bit, which gives us a much bigger number.
Which gives us a much bigger
0 to
number.
65,000 roughly.
0 to 65,000.
So much higher resolution.
So much higher resolution.
It uses USB 1.1, which means it's going to work with most USB devices.
It's going to work with most
it has
USB
a host,
devices. It has a
which
host,
is really good. It's the host device,
which is really good.
So
it's
it
the
allows
host
us
device,
to connect it very
so it allows
easily
us
to
to
our
connect
computer.
it very easily to
and this
our
is a
computer.
big plus.
And this is a
because
big
this is
plus.
something
Because
that makes
this is
it
something
much easier
that
to
makes
look
it
at
much
and address
easier to look at and address when we're using
Inside of here, also there are interrupts
Inside of
in
here,
here.
also there are
Here's
interrupts
the
in here.
processor 0, processor
Here's the
1. So
processor
there's two
0,
processors.
processor 1. So there's two
interrupts
processors.
in here. There's a few
interrupts
things in here that aren't necessarily
There's a few things in here that aren't
that are
necessarily
part of the M0
that are
chip.
part of the M0
But now
chip.
that we have dual processors,
now that we have
it
dual
allows us to do a
processors,
little more with it.
It allows us to do a little more with
couldn't
it
do with other ones in the past.
Couldn't do with other
and
ones
again,
in
we
the
have
past.
all our RAM down
And
here.
again, we have all our RAM down here. We've got
I/O
some programmable
to talk
I/O
to these
to talk
basically
to these
30 chips, 30
basically
outputs.
30 chips. 30
and we have an
outputs.
SWD. This
And
is
we
a
have an
programming
SWD.
port.
This
is
is a
used for
programming port. This is used
talking
for
directly to things like debuggers and that
things
for
like
people that are interested in that kind of
for
stuff.
people that are interested
When you're
in that
into it
kind
and
of
you
stuff.
want to break down the
When you're
code into
into it
high
and you want to
detail,
break down the code
you want an
into high
SWD
detail.
connection,
You
which
want an SWD
actually are the
connection,
three
which
connections
actually are the
that are
three
on the
connections
end of the board.
that are on the end of the board.
And I'll show you where those are shortly. I'll show
And
you
I'll
where
show
all
you
this
where
stuff
those
is.
are shortly. I'll show you
And the
where all this stuff
QSPI
is.
is the
And the
dedicated
QSPI
SPI
is the
port that talks
dedicated
to the flash.
SPI port that talks to
And
the
this
flash.
particular one,
And this
when they
particular
go down
one,
through here, they talk about
when
it.
they go down through
This
here, they
particular
talk
one
about
has
it.
2
This
megabytes
particular
of
one
RAM
has
attached to
2
it.
megabytes of RAM
That allows us
attached
to use
it.
it on the flash chip.
That allows us to use it on the flash chip.
So it actually works out really good.
So it's
and this
actually
just goes
works out
into a
really
little
good.
bit further
And this
detail
just
about
goes into
what
a
these
little bit
different
further
functions
detail
are.
about what these different functions are.
Further on in this book, they talk about
Further
minimal
on in this
design.
book,
This
they
is
talk about
based
minimal
on
design.
open
This is based
architecture.
on open
So this is
architecture.
open source. This is
So this is
allowing
open
other people
source.
to
This is
very
allowing
easily
other
use
people
their chip,
to very easily
which is
use their
actually
chip,
making it
which
very
is
popular.
actually making it very
in the
popular.
world now of microcontrollers,
In the world
we're
now
finding
of
that things are becoming
microcontrollers,
very
we're finding
open
that
hardware,
things are becoming
both
very
in
open
design
hardware.
and in software.
Both in design and
what
in
that allows
software.
us to do, it allows
And what
for
that allows us to do, it allows
quick building of items,
quick
but it also
building
allows us to
of
have
items,
a larger
but it
variety
also allows
of
us to have a larger
microcontrollers that are
variety of
available to us,
microcontrollers
which we
that are
haven't
available
had
to us. Which we haven't had,
which we didn't have in the early
in
days.
the which we didn't
If
have.
you look
in
at
the
this
early
basic
days.
design, this is
If
like
you
a
look at
bare
this
minimum
basic
design.
this is like a bare
This
minimum
here is your
design.
power control.
This here is your power control.
This would be your QSPI. This is your memory chip.
QSPI. This is your
This
memory
is the
chip.
actual processor chip.
This is the
crystal
actual
that
processor
sets
chip.
the
This is
speed.
the crystal that sets.
So
the
all of these
speed.
things are important.
So all of these
they
things
give you
are
all
important,
kinds of detailed
and they
file.
give
I'm
you
not going
all
to go
kinds
into
of
all this stuff
detailed
here.
file. I'm not going to go into all this
Power
stuff here.
is regulated in here.
Power is regulated
and basically
in here.
what it looks
And
at
basically what it looks at
there are two voltages that are of
there
concern
are two
to us.
voltages that are of
One is
concern
that it's
to us.
3.3 is for
One
all
is
the
that it's
I/O.
3.3
It
is
is
for
not
all
a
the
5
I/O.
volt board.
It is not a 5 volt
So if you're
board.
used to using
So
5
if you're
volt devices on an Arduino,
5 volt devices on an Arduino,
but some boards
but
have the capability of also working on 3.3. If they do, they will work with this board properly.
they will work with this board properly.
If it's an input device that only
If it's
inputs
an
a 5
input
volt
device that
signal
only
to
inputs a 5 volt
the
signal
input
to
pin, don't use
the
it on
input
this
pin,
board. This
don't
board
use
is
it
not
on this
capable
board.
of handling
This board
5
is not
volts.
capable of
It is a
handling 5 volts.
3.3
It is a
volt
3.3
pin on
volt
the
pin
I/O.
on the
And internally,
I/O.
it uses 1.1
and
volts
internally
for
it
the
uses
actual
1.1 volts
processors
for
and
the
inside
actual
digital chip.
processors and
And this
inside
is
the
all
digital
regulated
chip.
through
And this is all
everything
regulated
that's built
through
into the chip and,
everything
and
that's
through a
built
basic
into the
supply
chip and
that
through a
gives us
basic
our
supply
3.3
that gives
volts.
us our
Takes our 5
3.3
volt.
volts.
This here
Takes
is our
5 volt.
USB connector.
This here is our USB
It takes
connector.
our 5 volts from our
It
computer
takes
or
our
our
5
USB
volts from
port,
our computer or our
converts
USB
it down
port,
to 3.3 to be
converts
used
it down to
inside of the
3.3 to
unit.
be used inside
And then
of the
inside of the
unit.
chip, it's
And
brought
then
down to
inside of the
1.1.
chip, it's brought down to 1.1.
Oh, it's echoing badly. Let me see if I can
echoing
fix
badly.
that.
Let me see if I can fix that.
And I think I know what it is.
And I think I know what it is.
No, that says that's off.
No, that says that's off.
Where else could I be picking it up?
Where else could I be picking it up?
I'm looking to see. It's echoing
I'm
badly.
looking to see. It's
We've
echoing
had this
badly.
problem before, and it was usually
We've had this problem before, and it was usually the.
If I cover that up, is that any better?
If I cover that up, is that any better, Bruce?
Probably echoing again, but I'll wait for your response.
Probably echoing again, but I'll wait for your response.
I'm not sure where it's coming from. It sounds like I'm picking back up feed.
It sounds like I'm picking back up
but
feed.
I don't have anything else playing.
But I don't have anything else playing.
If I do that... Okay, that first try was not good. We had this problem once a long time ago, and I'm trying to remember what changed. Okay, so maybe... Let me try that. I don't know if this is going to be any better. Okay, let's try this, Bruce. You can tell me. I know trying to work out audio problems, but it'll make it much more reasonable if we're doing something later. There's a latency in getting a value back. I turned off my local speakers to see if that was better. Can I get a thumbs up, a thumbs down, or a yes, no from anybody? I'm hoping this is working. Oh, but not the repeat delay. Well, that's better anyways. So let's continue with that for now, and we're going to have to, hopefully, I can figure out what's going on for another day. We'll see if this works. So what I was saying here with the power is it takes your USB power, and okay, that seemed to fix it. I had to find another setting to click. And 5 volts goes into here, is regulated down to 3.3, then the processor itself converts it down to 1.1 for itself. They also talk about lots about capacitors and how you should design it, flash storage for adding it, the oscillator, how to set up the I/O, where to put resistors to make sure that they're working properly for communications channels, how to configure all of this stuff. They actually give you full schematics. They give you a ton of information. So it's actually a very good document by all means. If you're into producing all of this, by all means do it. And they talk about some of their specialty cards. When you get into the Pico, they have a separate data sheet to look at their board. And we're going to talk about this slightly. And basically what happens in here, as I scroll down here, they show you the 2 sides of the boards, which I'll show you in a little more detail. They talk about all the different things that are on here. They talk about some pinouts, which I have another diagram for. And they even talk about the mechanical standards. So if you wanted to make a frame to hold this, you have all the detailed measurements of where everything is located and what to do with it. They also talk about the pinouts, what the pinouts are on the chip, and what does what. So let's have a look at the chip then. I think this is where we really want to be just before we get into the programming of it. So let's do that. And what we're going to look at is this picture here. In this picture here, what we can see is these are all the pins. Now this is pin 1, way up here by the USB connector. And then we continue on down through here and come around to this side, and there's 39, so this is 40. This is 40 connections along the outside edges. These ones are your SWD connection for debugging it. These are the 3 pins that are used to connect there. So only if you want to talk to the processor and see the inside guts and see the coding, that's where the debugger would connect, and you would hook up and run a special program to see that data. This is the front of the board. Now what we want to look at, let's see if I go the right way. I did. This is the back of the board. This gives you the idea. This is an American quarter. These images, these couple of images are from Adafruit. I also have images from SparkFun and things like that as well. This is the back side of the board. And unfortunately, here's what tells you what all the connections are. If we look up here at the corner, we'll see GP0, GP1, and ground. Well, they obviously couldn't put the label right beside it because of the mounting hole. So this is actually GP0 way at the top. Then GP1. And this is something that's pretty unique and is visible from both sides of the board on the Pico. These are rounded around the pins. These are square. Hard to see at first when you first look at it. But those, everywhere you see a square pin is a ground connection. So, and they put lots of ground connections on this thing. In fact, they put it in groups so that you can actually get a ground close to your input or output to create less noise in the system. So this is what's been done on this chip. Now, the other thing you'll notice with this pad on the bottom, it's not just a circle with copper around it like we're used to seeing for a lot of our other stuff. Up here we have there's the square pin, and then we move down here to another square pin and so on. Like I said, that's the ground pins. But all of these have a round edge, or they just don't have the circle of copper around them. They also have this partial cutout of a hole, and the copper actually goes in right into that curve. This is getting to be a popular idea on designing a board that has nothing on the bottom. And the reason for this is because you can actually create a printed circuit board, and then you could surface mount this onto the other circuit board. Because you can actually solder all of these together, normally using a hot airflow, but you can do it with an iron as well. And you can actually solder these 40 pins to 40 spots on your own custom board. So it allows you to directly link it to that board. And because of the flat bottom, it doesn't interfere with anything else, and it has a very low profile. This I'm seeing on more and more boards that are being created, like I say, that have no components on the bottom. Don't worry about these test points. These test points are primarily for when they're setting these things up to make sure it all works properly and to make sure that it communicates the way it should. You notice a couple of them are up here by the USB connector, so that takes the place of the USB. We've probably got either power or ground here, and then a couple of the others, and they can test each board as they're produced. Okay, so that takes you into the board. This is what we're going to be using today when we start working with this here. So this is what I have on my printed circuit board, on my breadboard that we're going to be using today. And I'm going to be doing all my programming with this particular setup. So here is the Pico down at this far end. And then what I've done here is I've just got my ground and my power going out. Have a bunch of resistors, and I have 8 LEDs. And I configured them in red, yellow, green, and blue. And I'll explain that when I get to it. And I've run jumpers to 8 of the input pins. Or output pins, sorry. These are just general purpose pins, but I've set them up as outputs. The resistors are just in series. These are 470k ohm, or 470 ohm resistors for the red, yellow, and green. Blue actually needs a higher resistance because it's so bright. This is actually a 1k resistor. So I've actually used a higher resistance on the little 3mm blue LED. And then I've also got some NeoPixels connected to it, so I'm connecting them to power and ground, which this actually is the USB power. So I'm actually using the full regulated power coming through here without going through the I/O pin. And I have one data line that comes from a data pin, a GPIO pin off of the Pico itself. And then over here I have a push button and that is run to ground, and I'm using that as an input so I can see when it's grounded, and I'll show you how I program that. As well as I'm using an infrared emitter with a resistor in line and a detector, and basically it's a split line, and it either gives me a voltage in or a ground in depending on whether it sees the signal or not. So that's the basic setup, and this will allow me to do all the programming tests that I'm doing. It says here for traffic lights, neopixels, and grade crossing flashers. I'll load all of those in, I'll go through them and walk you through the steps of what's involved in the programming. So this is pretty straightforward. Now, another little thing that's talking about here, and I'm going to talk about that when we get to the traffic light circuit, because that's what this button is about. So we're going to talk about that in a little more detail. There's some features that are part of this board, but are not part of CircuitPython yet. And I do say yet, because it is coming. Because Pico, the Raspberry Pi people have put out so much information about this chip, other people are making boards to go with it. This is a SparkFun board. This is one of their prototypes. This is in the Feather format, which the Feather format was done by Arduino. But they have the boot button, and they have a reset button on here. They have a spot for a power supply. They also have their quick connector, which allows us to connect up I2C devices. And here's the Raspberry Pi chip itself and the crystal beside it. Or is that might be the crystal at the end, I forget which. But then you got the RAM chip, you've got power supplies, and a few other little things it needs. So everything is in here. So that's one of the boards they're making. They're also making this micro mod board. This fits into a series of boards where you can actually put different things in the top of a board. So this is their mounting system. It's actually screwed down at this end with a screw to hold it in place. So this is their RP2040 version of that. And then they also have their own miniature version, again, with these special connectors on the edge because the bottom's clear. And here is a smaller board that they're making along their quick, with their quick connector on the end to connect to I2C devices. This one is an itsy bitsy format from Adafruit. This is designed on their line of smaller boards. They're kind of their intermediate boards. This uses the Raspberry Pi 2040 as well. And again, it has two push buttons, one for boot loading, one for reset, and a number of the input and output pins along the edges of this, as well as power and ground. And the last one that I have here is their Feather format board. This is where they come in with the Feather format. You can see they got all their labeling here. They've gone down each side. You got a memory chip. You've got this here. This is the SWD connector, so you can actually solder one on if you wish to for troubleshooting. It has two push buttons, a quick connector, and a battery connector. This allows you to connect a LiPo battery, and it will charge it up. So you can maintain your project that way. And a LiPo battery puts out about 3.7 volts, so it can be regulated down to 3.3 quite easily. Lots of choices when you come to this kind of stuff. And we're going to have a look, and I want to have a look at the pinouts. And I believe that's in this direction. There it is there. Because we're going to talk about the Pico, and this is the one we're hooking up. So I want to go over a couple of things that are here. There are lots of pinouts. Everything with a yellow is a general purpose pin. There's lots of them. There are from 0 to 28, so there are 29 of them available. They are 30 general purpose pins, but the trick is with this one, only 3 of these, and they're on this side, on the right-hand side, is analog 0, analog 1, and analog 2 are available. There are 4 digital to analog, or analog to digital converters, but only 3 of them are accessible from the pins. The other one is used internally, and it's used internally for the temperature sensor that's inside the processor. So they only bring 3 of them to the outside to connect. The rest are all connected, and as you can see, we have many choices on here. We actually have green is pulse width modulation, so these are possible for pulse width modulation use. Almost every pin. Adafruit puts in here, do not use general purpose input 15. The reason for that is that this is used during a special cycle during startup, and CircuitPython is not happy with that pin. So they've been warning us not to use it with CircuitPython. It seems to work fine in MicroPython. It seems to work in C and C++, which C and C++ is its native programming language. MicroPython is put on as a way to run this, and it actually attaches the features, and it doesn't seem to have a problem from what I'm seeing running GP15, but CircuitPython does, because this goes through a special pull down or pull up during startup, which can affect its use if you connect it to a device. We also have all the clock settings, all the communication ports, and then true transmit and receive ports all over the place. So lots of functionality with this thing. So we should not have problems finding pins to do what we want to do. And that's what it's all about. So let's turn that off. And let's get into some programming. I'm using this picture right here. Let me zoom in. We're going to get started with this that way. What I see here, this is a basic traffic light. So what I have here is I have my red, yellow, green, and that's actually blue, even though it's hard to see. So there, it's lit up. You can see how bright it is. But what these are, this represents the stop, yield, go, and I'm using this as a walk. So we can see the walk and the green are on at the same time. The walk will go out. Shortly after, we'll go to amber. Then we go to red, and they're all red, and then the other cycle starts. So this would be like your north-south lights. This would be your east-west lights, for instance, or the other way around. And this is your basic traffic program. So let's have a look at how I built this thing and what we had to do to make this happen. So I'm going to go in here and open up my new software. And here it is. This is our basic traffic light. So right up here at the top, I've included my usual documentation to say what it is. Basic traffic lights by me. And this is run on a Raspberry Pi Pico RP2040 using CircuitPython. And this I used 6.2.0-beta.1. Now, a little bit about this. And this is going to be important for us as well. If you're using CircuitPython, remember I said this board, the Raspberry Pi board, was designed to run with C or C++. That's its default language. If you want to run it with MicroPython, you have to install what they call a UF2 file. If you want to run it with CircuitPython, you run a UF2 file. So let me show you very quickly why we're here. We'll stop at this point. Let's go get that information and have a look at it, where we find it. So what I'm going to do here is I'm going to go back into my Documents page. And on my Documents page, I have a page called CircuitPython, and it's just circuitpython.org. This is how we get started in CircuitPython if you haven't used it before. When you were at the board equals super clean. It is a clean board. I'm not sure what you mean by that, but that's okay. Oh, here we go. At the laptop, the faint echo. Oh, interesting. Okay, so we are here now, and what I'm going to do is I'm going to click on the Downloads page. And if I click on the Downloads page, we can see all the boards that are supported by Adafruit with this CircuitPython program. And there are literally boards from all different manufacturers. And they're not all done by Adafruit by any means. In fact, a lot of them are done by other parties. So these are some of these companies I don't know: J&J Studios, Electronic Arts, Damon George, Target, not to be confirmed with the store. Here's by Arduino. Arduino has it. That's that Nano 33 IoT. That's capable of running CircuitPython. So all of these boards have what we call custom configurations. Now there's a lot of boards on here, so what I normally do is search for the board that I want, and I want the Pico, and there's 3 different Picos. But this is the Raspberry Pi Pico. This is the one we're using here. So when I click on this, we can actually get the latest UF2 file, which tells it how to operate. And this is now 6.2.0-beta 2. I have beta 1 on my particular board. So they've made a couple more improvements in the beta version. When it goes to full-blown release of 6.2.0, then this will no longer be beta, and it will be the full-fledged distance, full-fledged program. And then the other things that we're going to look at, so we can click on that, it would grab the information, and it would allow us to then download it. And I'll show you a little bit more about that, although I'm not actually going to do it on this chip, but I will show you what it will do. I will talk about that. The other thing we need to do is we need to bring in some libraries. So if you click on the libraries button up here, here's the version 6 bundle of the library, the latest version. And this one's actually dated today. Look at that. 2021, February 14. So there's been some updates since yesterday. So they've actually run another version of it this morning. And these update all the time. Now, what exactly has been updated, you can go in and look at. It may or may not affect you. I'm using one from about the 7th or 8th of the month. And it will work fine for what we're doing today. So let me turn that off, and let me show you how you would install CircuitPython. So over here, when we look at our file system, I want you to notice this board down here. There's a white button on here. And let me just open up the file system. When we open up this file system, I'll see right down here, this might be hard to see, it's a little small, but it says CircuitPython G is the drive. This looks like a USB device to my computer right now. When you first buy this board, you plug it in, it'll actually say RP- I think it's 2040. And that is because that's what the board is programmed with from Raspberry Pi organization. Remember I said that it had one thing it had in the USB, it had both a host and a device capability? Well, this allows me to plug it in and I can see it right away without any special software. I can look at the board. So to download the UF2 version, I would go over here to my file system, right here. So here's the G. Normally that would be RP2040 when it's brand new. What I would do is, if I see something here, if it says RP2040, it hasn't been set up yet. So you can unplug it from the USB, hold down the bootload button, and then plug it back in. When you're holding that boot start button, when you're holding it down, it puts it into another mode. And it says, hey, I'm ready to accept the file. And what I've done here is if I come down here, I have this long file. This came from the download site, from the CircuitPython.org site. So this is the Adafruit CircuitPython Raspberry Pi Pico English US 6.2.0 Beta 1.uf2. UF2 is a standard that was actually created by Microsoft for this type of purpose. And all I would do is grab that and I would drag it on top of the drive. And it would reboot the drive. It would load in the basics of CircuitPython. And when it came back up, it would say CircuitPy and then the drive letter, whatever it is on your computer. So that's how we get it started. And let me show you a couple of things when you do that. We're going to switch out this program for the traffic, and I'm going to show you a default program when we're ready to. So this is all good. We're ready to go here. So let me just turn that off and let us get back to the program. And there we are. So our basic program up here. When we're doing this, we want to import some helper files. We always do this. Now I just have to import board. What that does is give me all the I/O pin capability, allow me to talk to the I/O pins. And it also brings in some other features that are internal to the board. It brings in a bunch of kind of standard commands. Time is a clock. It just allows me to bring a timer into the program. And then there's also digital I/O. And digital I/O allows me to set up all my pins as digital pins, either inputs or outputs, depending on what I want to do. Then I create the onboard LED. This chip does have an onboard LED up here in the corner, right beside the USB connector. It's very small. But what I have here is LED is equal to, and I've created it, digital I/O dot digital input and output board, and it's GP25 is that connector. And that's shown on our reference chart we had. So just to remind us what was on there, We can go back to here. This LED that's located way, way, way up at the top is listed as GP25 LED. It can be used either as the GP25 name or the LED name. It's actually predefined, which is kind of nice. So we can do that. So just turn that back off. In here, I've created a bunch of other tags. These are just tags I've created at the beginning there. I call it LED, and I used it as output. If I change this GP25 to a capital LED, it would work exactly the same. That's what's shown on my pinout diagram. Down here, I've got my other ones. I've created an LED east-west red, LED east-west yellow, and so on. And again, the second line off of each of these is telling me what I want to do with it. And these are all direction output, which is all pretty straightforward. So what I'm going to do now is I'm going to go down here. There's a print statement here that says running the traffic lights. Print statements produce information back out onto the USB cable. It's not being printed to a display. I don't have a display hooked up to it. I turn on my LED light, I turn it off, and I look at false. Down in my program, just to give you a real quick synopsis of what I'm doing here, while true is the main program in CircuitPython. In Arduino, if you were used to that, you would be using void loop with the brackets behind it. And that would be the same thing as while true. I've created an if a step is equal to 1. I want to set my initial set for position for all my lights, for all my LEDs. I'm turning on the 2 red lights, 2 LEDs, and I'm turning off all the rest. I pause for 1 second, and I go to step 2. When it's equal to step 2, I turn off my 1 red LED, turn on my green and my walk. I sleep for 4 seconds, then I turn off my walk, sleep for 2, and then I move to the next step. This is where I go to yellow, I go to all red again, I go to north-south green, I go to north-south yellow, and then it just loops back because it gets it back to step 1, which brings me back to here. So this takes care of all my traffic lights. Very simple, nothing difficult in here, and I'm working a bunch of LEDs. If I want to see what's happening here, I can open up a serial device. This is my serial device. This program works, so all I'm going to do is hit save, and we're going to see that both this LED is going to work on the board. All these lights are going to get reset, and I'm also going to get some information up here on the screen. So I'm going to hit save, and when I do, it told me it was rebooting. It says running the traffic light. That's that print statement. My LED actually went on and off, so let's try this again. I'll hit save again. This time we'll watch the LED down here in the corner. There's my LED is on, and then it's off, and then my traffic lights continue to go. So very, very quick, it actually works, and it's working really nice. This is a basic little program. I haven't done a lot in here, but let me show you more of what it looks like if it's brand new. Because all of this stuff is not here when it's brand new. In fact, I'm going to take all of this out. I'm just going to highlight. I have this saved in another place, so I'm not too worried about it. I'm going to delete that, and I'm going to put in what's in here. When you buy one of these, this is what's in here. Whoops. Let's put the right thing in there. That should be one of those. Hello, world. Gotta get my fingers to work the right way now, and we'll be set. That is what's on the chip when you first download CircuitPython. So when you open that up and you hit save, it comes down here and it says code PY output, and it says hello world. Code is done running. That's it. That's all it does. That's what's going to happen when you first load CircuitPython on. Now, these modules like board, time, digital I/O, and there's many others, I want to know what they are. So I'm going to show you how to do that here at the bottom. I'm going to come down here and it says Control D to reload, but it's Control C to break. And what happens is here, it's now telling me that I'm using the Adafruit. In fact, let's bring that up in size a little bit. And I'm using an Adafruit CircuitPython, and it's telling me what it's running on. Raspberry Pi Pico with RP2040, and then I have this triple arrow. This allows me to enter commands directly in here. And one of the ones you can do in here when you have a brand new board that's done with CircuitPython, I'm going to go in here and I'm going to type in help, and I want to know what modules are located on this board. So what I'm going to do is here, I've typed in that help modules, and I'm going to hit enter, and I'm going to increase the size of this. And here's the information it's given me. There's something called --main --bleio --pixel buff. But then there's an Adafruit bus device. Adafruit bus device is used when I'm talking to I2C devices primarily, or other communications. There's a NeoPixel write, analog I/O, but here's board. That's where I got that word board from that I was importing. That gives me the ability to import something. I also imported display I/O, and here it is here in the list. As this continues down here, you'll see there's JSON files, math files, microcontroller if I want to look at the internal clock on the chip, pulse width modulation I/O, SD card, and way down here was time. There's also touch I/O, and there's ULAB, and you can actually go to the USB devices because it can output information too, like a MIDI player, or make it look like a keyboard to the computer. So if you look at all of these different things, these are what's built into the basic systems on the board. So what we do is we usually go a little further and we start opening up other files. And I'm going to do that. And I'm going to make myself real simple because I'm going to actually just copy and paste a file that I have. And this one's actually a little bit longer because I made it more than just simple. And I'm going to show you what we do here, and I'm going to paste that in. And let me shorten this window down here at the bottom, and I can scroll up to the top. I've added some comments in here. This is a simple LED and reset. I've already created these programs in the past. Again, this is board, time, and digital I/O. Here's my LED pin that I'm using. Here is a push button. So this is the push button that's down here on the board. So that's this push button down here, I think. Let's see what pin I connected it to. I connected it to 16. Let's change that to 17 so I can use it on the push button. Otherwise, it's going to use my infrared. This case here, I'm using it as an input. And then what I've done is I've gone to push button 1, pole equals digital I/O, pole up. What that does, it applies 3.3 volts to the pin, but through a resistor. So now I can ground it, and by grounding this pin, when I push the button, it actually connects through these black wire, the black wire here, and goes back to ground. I actually change the voltage to 0. I've created some timers here to do this really nice. And what I have in here is I just created some timer values, and I've added decimal places because I want this to include milliseconds. The default timing for CircuitPython is in seconds. So that's 0.000 seconds, and so on. And I'm going to turn my LED off to do it for starting. I'm going to do a line that's going to print on my serial monitor down here, or the REPL, as time to start, and then I'm going to get into my main program. And the first thing I'm going to look at in here is current time. I'm going to make it equal to time. There's where I'm using that time function. Monotonic is the amount of time that has elapsed since this chip was turned on. That's what that number is going to represent. And then when the button is pressed, what's going to happen here, if not push button 1 value, because remember it's got 3.3 volts on it, so right now it's true. This means if it's not true, so in other words, if it's false, take the LED value and make it not the LED. In other words, toggle the LED. If the LED value is true, then LED on is equal to true. Print current time. So I'm going to actually display how much time has gone here. And then I'm going to reset my reset timer, and I'm going to add my delay time, which was 10 seconds, and I'm going to pause for a half a second leaving this. If the LED is off after the time delay has finished, so if PB1 is true, in other words, I'm not pressing it, and the LED is on, this is this onboard LED, And if the goal time is less than the current time, so current time is past our goal time, we're going to turn our LED off and we're going to turn our LED on equals to false instead of being equal to true. So let's save this. I'm going to just bring this window up a little bit more so you can see some information here at the bottom. And I'm going to hit save. And it should have saved. Oh, I got to get out of this. Sorry. Control D to get out of that. Okay. So now it says code PY output, time to start. So now let me reload that again so we don't have to reload that, but we can watch this LED light down here in the corner. I'm going to press the button. My LED light comes on. If I press it again, it'll turn off. And on the screen here, tell me how much time elapsed. So I had a little over 3 seconds. Turn it on, turn it off. That time a little less than 2 seconds. If I turn it on and leave it on, this is where I have the auto reset on its own. After 10 seconds, it will shut itself off. And when it does, we're waiting. There it is. It says it's finished, and the LED went off. Actually, I guess I could add in here, when it goes false, let's take that print. I'm going to copy that statement. I'm going to show you how we add programming to this real quick. I'm going to add in the current time. I'll save that again. There it is. Press my LED button once to start it. My LED's on. I turn it off. Now I'm going to turn it on and leave it on. And what it should come back with is a time approximately 10 seconds after what I had. And there it was. In fact, look at that. Now how much closer to 10 seconds can we get? That was pretty fast. Like we got it down to a single decimal point. Try it again. This time it said 95, so it should be 2:05:38 if it's 10 seconds. Okay, 2:05:38. Looks like it worked. So that's working fine. Now, we talked about something here, and I said I would mention it again when we start using the push button. If something is busy, and we were to supply an input to this board, and we're using one of those time.sleep commands, the program's actually in hold pattern during that time. Interrupts are something that we've used in the Arduino with the old Atmel chips, and it actually had the ability to do interrupts. And the interrupt allowed us to supply an input regardless of what was going on in the program. We can do that differently, but we can do something similar on the new RP2040 chip. In MicroPython, we've always had this problem as well, as because of the chips that we use, typically aren't the AVR Atmel chips. So because of that, they only have one processor in them, and they don't have designed interrupts built into the chip. What we do in the RP2040 is, remember we talked about this, and it said we have 2 processors in here. It's got dual M0 plus processors. So what we do in MicroPython does this now, and so does C and C++. You actually run, this program, for instance, could be running on one of the processors. And then what we do is we write another section of code that would run before this one that tells it how to use the other processor. And in the computer world, we're really used to this, and this is probably why Raspberry Pi did it this way, is because it's called threading. Threading is very common in the PC world. Threading is used so you can run multiple processes at the same time, each on their own processor. And that's exactly what happens when you're running an interrupt. Is it's something that's running in the background on another processor, not your main processor. But it can supply input available for the main process. It also has the ability to use all the same inputs and output pins as the first processor. This is something that CircuitPython has not been able to do because they've only run a single processor that does not include interrupts. But with this new chip, they are now looking at ways to program in and use threading in CircuitPython. They haven't got it working to the point where it's ready for release, but it is something they're working on and will be out in a future release of CircuitPython. So we are going to have that ability before long. And that will allow us to use it like we did interrupts. The biggest thing for interrupts, if you want to do something like high-speed recording of rotations, for instance, you want to do an RPM counter and it has to count a high-speed encoder, you couldn't do that unless you had a separate processor for it. So this will allow it to use the other processor to do something like that. And then write those values to global variables that can be used by the program running on the other processor. So they can run independently from each other. So it will look like high-end interrupts. That will be a big, big boost to what's been going on. So that's what we're moving towards. But that allows us to take our programs and make them much more complex over time. So we're just starting out with basic, simple things here. Let me load in a couple of others really quick because we're running out of time. We're getting close to that hour. So what I'm going to do is I'm going to open up one here for my, I did the traffic lights. I've got this going. Let me do the NeoPixel one. So I'm going to open up this code here. I'm going to copy over my NeoPixel code. And basically what I'm going to do is I'm going to overwrite all of this code in here. So I'll just highlight all this code. And this is just basic Windows commands, so copy and paste. And I'm going to paste over here, and I'm going to go up to the top. And I'm going to show you what we have going on. And this is our NeoPixel strip on here. If I tilt this slightly, you'll see that there are 8 LEDs on there that are programmable. So I just want to show that it can run NeoPixels. So this time I import port, I import time, I import digital I/O, I import NeoPixel, which is actually a library file, so we put that in a library folder on the drive. And because it's not part of the root stuff that we had, and random, which is part of the root. Pixel pin, I'm setting up board GP22. So I've actually got this white wire over here that goes to the NeoPixels, and it's connected to general purpose pin 22. And I've given it the number of pixels, and then I create the object. So this is strip equals NeoPixel.NeoPixel. Pixel num is 8, and number pick is 22. So it's going to go to general purpose 22. I've created some basic colors, black, white, red, green, blue, and yellow, and mauve. I've created those on here. And I've created them into an array. So I've created an array called colors, which position 0. So array colors square bracket 0 would be black. In other words, turn them all off. And then I've got white, red, green, blue, and mauve. So I've actually done it by the number, by the letters, and I've created these arrays. First thing I'm going to do is turn off all my NeoPixels in case they were on. I'm going to put down a message at the bottom here saying testing NeoPixel. I'm going to pause it for 1 second, and then this is the whole program. What I'm going to do is I'm going to create a random number based on a range from 1 to 6. 1 being white, 6 being non-existent. Well, the way it works is the maximum minus 1. So it actually goes from 1 to 5 in intervals of 1. So it's going to include 1, 2, 3, 4, 5. It's going to come up with a random number of 1 to 5. And what it's going to say is in the range of 8. So my strip, position 0, is the one at the bottom of this strip. And then we're going to have all the different colors, and then we're going to sleep. And let's change this so we can actually see it at 0.2 of a second. Then we're going to fill it with black, and we're going to sleep again. But the color is going to be random each time it writes to the NeoPixels. So let's try this. We're going to see down here, testing NeoPixel. And if I tilt this slightly, so you can see it, you can see they all light up one at a time. And there's green, for instance. Looks like we're doing blue. Blue again. Red. That's kind of a yellowish color. I don't know. We don't have yellow in there. That must be the white. Blue. There's mauve. So we do go through and we light up each of the pixels. We can slow this down. We can make that 2 seconds. Hit save. This is part of the beauty of CircuitPython. Look how quick I can make changes to this program. Now we can see each one lights up in 2-second intervals till it gets to the end. Last one will stay on for 1 second. It'll all go dark, and then it'll start and they light up with whatever random color it chose that time. So I think that works. I think that works very well. And we can speed that up or slow it down so we know we can have our marquee lighting. We can create different animations. We can create patterns. We could turn on one light, then turn it off. So we could create a random position as well as a random number. So we'd have lots of choices on what we want to do here. So this is the starting of a lighting circuit. This could be used in our model railroading world. We could use this for picking up lights within a building and turning on and off lights and different things at different times. So that's our NeoPixel. And I'm going to go to my last program because it is the most complicated of all of them. And I'm going to do my grade crossing. This one is a fair bit longer, but that's okay. I'm going to walk you through it. There we go. Copy. I'm going to go over to here, and I'm going to highlight all this code, and I'm going to write it in here, and let's have a look at what's going on. This one's a lot bigger. This is our crossing lights. I've done this before with CircuitPython code before. So this isn't anything new except this is now on the Raspberry Pico. Include the helper files, board time, and digital I/O. That's all it needs, the very basics. Again, I've created my LED on board, and then I've added all my other LEDs. Now these would normally represent the crossing lights. So on a crossing light you have two reds, then it moves to the other two reds, two reds, two reds, two reds, back and forth. We're going to simulate that, but I'm not going to change the color of the LEDs, just because that would take more time than we've got. And then what I'm going to do is I'm going to create two sensor inputs. One is my push button. That's sensor 1. Actually, that's sensor 2. Sensor 1 is this infrared. This is an infrared pair. So this would be placed one on each side of the track, so when the train runs through it, it blocks the beam. So I've actually created these already in here. I've created some time delays to allow things to do. 0.45, this is my phase delay. This is how much time goes between the toggling of the two reds back and forth, and we'll see that. I'm going to print there, enable grade crossing. I'm going to make this LED true just to tell me I've booted up the board. And then what I've got is I've created some subroutines. These are definitions, one called all off, which basically just turns all the LEDs off. Then I have phase 1 for the LEDs, where half of them are true and half are false. And then I've created phase B, which is the opposite are true and the opposite are false. And I've just started the program with all off, which makes sure that all these LEDs shut off the first time I turn them on. And then I'm going to go down here, while true, and it's going to say get current time from the clock. And then what I'm going to do is I'm going to start cycling through. If one of my sensors are tripped, what happens is we start making the lights flash. We keep them flashing all the time. Once we let go, what did I set my delay at? I set it for 6 seconds. So once there is nothing blocking either the infrared or the push button, this would be a second set of infrared normally, one on each side of the grade crossing. And once those are not being tripped for 6 seconds, then the flashing lights will turn off. And that's basically what all of this does down below. So let's load this in and see what happens. So I'm going to go ahead and load that in. Now my NeoPixels probably aren't going to shut off because I didn't turn them off before. Let's just tilt that forward and make it less obvious. So what I'm going to do now is if I press the buttons, we can see my lights go back in that alternating pattern. And I don't have to hold it. 6 seconds later, they'll stop flashing. Okay, and I can do that again, and it will do it. If I press it again, each time I press it, I'm also getting this LED down here telling me that something's interrupted the signal. So every time that turns on, it resets the timer to another 6 seconds. So eventually it will shut off. So that says each car is passing the sensor. It also works with the infrared. So I can do it without touching a push button. And we can see here again that as I go through here, the LED is shutting off and turning back on as each car passes. When it's finished after 6 seconds, it shuts off. So that works for our model railroading. So for our model railroading, since I'm involved with that quite a bit too, we see we've created traffic lights, we've created custom lights for buildings, we've created grade flashing crossers, and we could create pretty much anything else we wanted to with simple outputs. Couple words of wisdom with this. This is a low-cost board. I didn't tell you how much it cost yet. It was introduced at $4 US a board, which is just remarkable when it comes to microcontrollers. Most microcontrollers are going to cost you between typically $8 to about $30, $40, maybe $50, depending on how detailed it is. But there are limitations for a $4 board. First of all, one of the limitations is it has an awful lot of inputs and outputs, which is actually a very good positive. The downside is it's very low power. It's a very tiny chip. If you notice on my board, each one of the LEDs is connected to a separate output. The reason is you only get about 19 milliamps per output pin. Very small, even for a microcontroller. That's extremely small. So if you want to control multiple items, you may wish to use something like NeoPixels, which actually take their source from outside of the board. They just take a signal from the board. Or you may want to consider using some sort of items. Like if you're going to connect a coil to this, whether it be a magnet, a solenoid, a motor, you're going to have to interface it with other electronics in order to make it work properly, or a relay or something along that line. It might just be as simple as a small transistor. But think about it that you only have limited current coming in. This board also only has 3.3 volts on these pins. They are not 5-volt devices. So make sure your devices work with 3.3 volts and you'll be okay for both inputs and outputs. All of these things are true when it comes to this. So you got to be careful when using it. It's not as robust primarily as an old Arduino board, but it's a lot cheaper. A basic Arduino board, typically you're spending $15 to $20 for one of them, US. Now, I know there's China knockoffs that are cheaper, but even those, by the time you get to it, this is the same money at $4 US. In Canada, I'm seeing them around anywhere from about $535 to $585 Canadian for one of these boards. Really cheap in the world of microcontrollers. You can still do lots with it. So don't discount it. Don't put it out as something bad. I think you'll find it's actually a very worthwhile processor to use for building simple projects and to learn some simple programming. You saw today I made a couple of changes to my program. I was able to implement it very quickly because it's connected like a USB device. CircuitPython is a great platform for learning. MicroPython works well and can take advantage of threading, but there's a higher learning curve to MicroPython. C and C++, you can obviously do even more to it because it's its native language. The problem is you have to compile it so you don't get real-time feedback. You have to go through a little bit more debugging when you're creating the files. It's not quite as friendly as CircuitPython. Arduino does not have an emulator for this yet that I know of for the RP2040. I suspect they will soon. There's been talk that people are working on making the RP2040 available to the Arduino language. I suspect it will be before very long, so you'll have that option as well. Nice low-level entry board, cheap price, can learn lots with it, and it is low cost. So I hope that helps. I hope everything that I've talked about today is important. There is my link now for my email on my YouTube account if you need to send me an email. You can send a comment through YouTube, although I don't see them usually right away. My emails I look at least once a day, so chances are you'll get a quicker response if you send it to that. So I do have an email link in my on my YouTube page now under contact information. It is there. If you want any of these programs, these are all open source. You can either do screenshots or you can ask me and I'll send you. These are all very small files. Typically, these are just a few kilobytes. Like we're talking really small kilobytes. I think this one here. Let's see, what's it say? I have that page open. It's 4 kilobytes, this program, for the grade crossing flasher. So it does give you some ideas of what to do and how to start building. There's more functionality coming from CircuitPython. The people there are actively working on updates. So we're going to be seeing more. I don't think it'll be long before we see threading. I think that's going to be a great feature when it comes. I'm looking forward to it because I miss interrupts in CircuitPython. So I think this chip will now allow us to do that. Do you have any more questions? Anybody happens to be watching? I've got my YouTube chat up. I haven't seen anything else new on there. I hope you've enjoyed it. So I'm going to put this up here. This was me. This was Kingernorth. Microcontrollers with Kingernorth. This was episode 27. If you're wondering where episode 26 went, it was actually a little bit of a Halloween video. Really wasn't a true lesson. But this is 27 to start out the new year. I will be back in 2 weeks. In 2 weeks, I'll be back on my Saturday program, and I'll be looking at another low-cost board that's called the QTPY. And it is programmable in both Arduino and CircuitPython. So I'll be showing it with both languages there. All right, until then, thank you very much. At Twitter, you can get me. I'm at Kingernorth if you follow me on Twitter. If you subscribe to YouTube, it's here on the channel you're on now, which is youtube.com/Kingernorth. By all means, let me know what you thought of it. I hope you've enjoyed it, and I hope everybody's had a chance to learn something. So until next time, have fun.